What is going on, guys? Welcome back to another video. In today's video, I will be proving the most famous equation in math. And yes, that is the Euler's identity. I mean, just look at this thing. It has e, pi, an imaginary number, 1, 0. I mean, where does all that come from? Don't worry, stick around and I will show you how we can prove this thing to equal each other. But just look, first of all, let's just take a look at this thing. We have e, we have pi, we have I, we have 1 and 0. These 5 numbers are probably one of the 5 most important numbers in all of math. And each one of them represents pretty much everything like in the history of mathematics. We have 1 counting number, 0 the element of null, and we have pi discovered by the Greeks, and then we have e with Euler's number, and then we finally have I discovered while I'm trying to solve cubic equations. So yeah, this pretty much wraps up all of math history into this crazy equation right here. So how do we even prove this? Don't worry, we'll prove it using 2 things that I linked down in the description if you are not familiar with. But these are the Taylor and Mclaren series, and yes, don't worry, it looks kind of complicated, but we'll go over it. If you want to know how these are proven, I have stuff in the description. Just look through them. Some people have already discussed how to prove these equations, but we're just going to assume this is true because it's already been proven to be true. But I'm just not going to do that today because otherwise it'll just take too long. But we are going to use these 2 series to prove that this equation indeed is true. All right, so let's do that. Okay, first, we are going to take a look at the Mclaren series, which if you know already, you can see is the Taylor series, but it's like a very specific Taylor series centered at x equals 0. So that's why we have the 0, and then the a disappears because x minus 0 is still x. So we're just going to use this, and we're not going to worry about this, but just know that this equation comes from this. All right, so first, let us try to prove that, again, Euler's identity holds true. I mean, obviously, just look at this. This is kind of like the fundamental definition of the complex plane and how it relates with the real plane and stuff. And I just want to bring up this Wikipedia page because I want you to see that we are going to use sine and cosine for this. This is kind of like a spoiler alert, but that's kind of like why I bring this up. So let us go and prove this equation true. All right. First, what we're going to do is we are going to find the Mclaren series for e to the z. Z because we're dealing with a complex, kind of like a complex number here. So e to the z, and what did I just do? I just reloaded the thing. All right. Anyways, ignore that. I just pressed the reload button. But e to the z equals. All right, we're going to try to expand out this series. But first, we need to establish the derivatives of e to the z at any certain point, which is 0 right here. So we're just going to say, just for the sake of the proof, but we're just going to make it formal here. Let's just insert an equation right here. And that'll be let f of z equal e of z. And what do we know about e of z? That is right, e of z never changes. The derivative will always be e to the z. So we are going to start listing this out first. So the first derivative, or I'll just do f prime of z. How about that? Equals e to the z. And you kind of get the point from here. So boom, boom. We're just gonna do a few just so you can get the idea here. So basically all of this is all e to the z. But remember, if we go up to the series here, we see that it's evaluated as 0. So if you just replace 0, we'll just evaluate this at 0, 0, 0. And this z, obviously replace that with 0, 0, 0, equal to 1, equal to 1, equal to 1. So you can see, it will just equal to 1. No matter what we do, e to the z, e to the 0 is just 1. So no matter how many derivatives you take, it just goes on and on. So I'll just do something like dot 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 dot. Yeah, just like it just goes on. So that's pretty easy here. We know that this term will always equal to 1. So let's simplify this for a second. So we can establish that e to the z equals the sum, and I don't know why it didn't escape there, but, and I'll retype it. Okay, e to the z equals the sum from n equals 0 or k, doesn't matter, to infinity, and then again, we're just using this Mclaren series right here. So what does this equal to? That's right, 1. So that means this comes up and it cancels out. So it just literally becomes x to the n over n factorial. Just like that. And let's expand this out a little bit just, for the sake of looking at what this is. So the first term, n equals 0, x to the 0 over 0 factorial, that would be 1, plus x to the first power, plus, we're going to need the fractions, x to the square, over 2 factorial, and then I'll just copy and paste a few more. So this will be the third, 3 factorial, the fourth factorial, and you know what? I'll just leave it. And because it's going to infinity. So yeah, that's e to the z right there. Alright, now let us do sine and cosine. Okay, the reason why I do sine and cosine, trust me, is because later on we'll see something pretty elegant here that will evolve sine and cosine. This is to make sure we get in the pi terms, because that's where the pi comes in. It's when we use sine and cosine. Again, it all makes sense later, but we're going to prove that. So, we're just going to do sine and cosine for now. And let's get this here. So we're going to let g of z equal to sine of x or z. Yeah. And then now we're going to get the first derivative of g. That's just cosine of x. Z. Again. Not x, because, yeah. Second derivative equal to negative sine x. Third derivative equal to negative cosine of x. And fourth derivative goes back to sine of x. Actually, no, wait. Yeah, fourth derivative goes back to the sine of x. So let's just do that really quick. I will just say this so that we know that it loops back to the beginning, which equals sine of x. So you can see all three functions, sine, cosine, and e, they all have repeating kind of like patterns for the derivatives. So that's why we use this to prove that this equals each other. So okay, now we know that sine of x equals the sum from n equals 0 to infinity, because we're gonna get infinitely accurate approximation. Okay, but notice something. We have positive, negative, and if we remember, we have to evaluate this at 0. Don't forget about this. We have to evaluate this at 0. So sine of 0, right? You have sine of 0, which is obviously 0. Cosine of 0 is 1, and then it's just negative 0, negative 1, negative 0, negative 1, 1, 0. You get a point. It just repeats, but with the negative form. So it's like 1, or 0. I'll just write it down because I'm tripping up on my words. 0, and then we have 1, and then obviously we have this negative sign here. So this is 0, 0, 0, 0, 0, 0, 0. So yeah, because we're using this series right here. But yeah, okay, and then we have negative sign. It's obviously negative 0, which is just 0. And negative cosine of 0 equals, and I don't know why it's defaulting back to x again, it's z. But it's just negative 1. So you can see we have positive and then negative. And then 0, and then the zeros cancel out. So that means we are going to have an alternating series, right? And then since every even term the zeros cancel out, we are going to have a odd series right here. So we're just going to fraction this. So that will just be x to the 2n plus 1 because it's odd. And then 2n plus 1 factorial. So far, this isn't anything too complicated. These power series are pretty well known. And just for cosine, I can go through the derivative process again, but these are inverted, so it's actually the even terms. So I'll tell you what that means in a little bit when I expand this out. So what does this mean? Okay, well this means x minus, gotta get the fraction out, x to the third, because the x to the second got canceled out by this 0 right here. Because remember, second derivative, right? Second derivative, second power, but the second derivative is negative sine of 0, which is 0. So that disappears. So we only get the odd, because every even term disappears. But remember, the next odd term must be positive, because we have this alternating thing with the negatives and stuff. So again, it goes back to minus and dot dot dot. Now for cosine, it's the same alternating deal. And let me just copy and paste this. Except for this is even. And x, again, x to the first power is odd, so it becomes 1. This is not supposed to be a 4, this is supposed to be a 2. So you can kind of see the pattern here with sine and cosine. So again, all of this just on the Mclaren series. If you didn't know what that was, check down in the description again, or I have it linked up somewhere in the top right. But yeah, so that is it. Now we are going to do the real proving part. So let us do something with this z thing here. We're going to copy and paste this down here. But let us say, z equal to, since it's a complex number here, right? We'll let it equal to I theta, because it's a complex, and then we're going to add an angle here. Okay, so therefore, this means that this will just become I theta. If I can type that right, there we go. This becomes I theta, because again, we're replacing every single place where there's the term with I theta, and then yeah, you get the point. So that kind of pretty much wraps things up for this. So now that we have this e to the I theta thing, and again, this is kind of like spoiler alert, but theta will eventually become pi here. But for now, we're just gonna do theta for now. So we get 1 plus I theta squared plus I theta cubed, and then and then just so I can make this proof extra clear, again, I'm just gonna write this out again just for redundancy, so that people can see where it's going and it's not some sort of magical trick or something. So exponent rules apply here. So this has just become squared, theta squared, and then the parentheses dissolve, and then you get the point. I cube theta. Do not think with that. I cube theta cube And I don't know why. There we go. I to the fourth. Theta to the fourth. So we just, again, exponent rules, nothing fancy here. So again, this is still e to the I theta. Nothing changed, and there's nothing against the rules here. We're continuing on. Alright, next, let us see what we can do here. You can see that I squared, what is I squared? Well, fundamentally speaking, I squared is negative 1. Negative 1. And what's negative 1 times theta? That's right, negative theta. What is I cubed? Well, I cubed is I squared times I, which means it's negative 1 times I, which is just, that's right, negative I. What is I to the fourth power? Well, that is I squared times I squared, because, again, it's exponent rules, right? I squared times I squared equals I to the fourth. And what is I squared again? Negative 1 times negative 1 is, that's right, positive 1. So you kind of get the point here. So this is, actually, I can just remove this. And then what's I to the fifth power? Well, it just goes back to I to the first power, because 1 times I is I again. So we get this thing here. We get negative theta squared minus I squared, and then, you know, just like, okay, you know what? I'll just write down a thing again. I just can't explain it with verbal communication. Symbols are definitely the best here, so I will just show you what I mean by this. Alright, let us do this here. So, this negative, we can minus this, and then this minus this, and then again that disappears, and this is a positive. And just for the sake of it, we are going to add a few more terms just so you can see where this is kind of going, because right now it kind of seems like a random pattern here, but I promise it's not a random pattern. Okay, so we kind of established that this is just I again, because I to the fifth equals I, right? So I to the fifth is just I, and then theta, where are you? There we go. Theta to the fifth. And this is a positive I, by the way. And then we go back to the negatives, because I to the sixth just repeats from this again. And it's just negative 1. I to the sixth is negative 1. Again, if you don't believe me, fact checked it somewhere. It's just negative 1. And then theta somewhere, you know, just copy and paste this. Oh, yeah. I already have negative subtraction right there. So this is just to the sixth. Again, negative here. And then, what would be the next one? Minus, that's right, again, we go back to this term now. Except for, it's for the seventh. And then, it repeats, loops back to the eighth term. Which, if anyone is familiar, the powers of I, they kind of just alternate on and on and on and on and on. You know, just a repeating loop. So this is what we have currently. Alright, now this is where it gets cool. So, let us take all the I terms and group them together, and then all the non-I terms and group them together. So, let's do that right now. So, again, nothing changed. We're just kind of rearranging stuff and doing some other stuff here. But 1, does 1 have an I next to it? Nope. So we just 1 plus, or minus, since the next thing that doesn't have an I term is this. The next thing that doesn't have an I term, because again, this has an I term, so this doesn't have an I term, is this. What's the next thing? Is this. What's the next thing? Is this. And then, oh, this supposed to be, yeah, plus dot dot dot. Okay, so let's group all that together. Again, we're just rearranging stuff, nothing changing. And then, okay, now, what do we do with all the terms with I? Okay, so let us plus, again, this has an I term. This has an I term because it's the minus thing. And this has an I term. And this has an I term. Kind of running out of room here, but you get the point. Dot dot dot. Boom. Now, since all of these have I terms, what do we do? Well, can't we just pull the I out? Just like factor it out, you know? Just that's what we're gonna do. So we're gonna leave this first thing alone, and the second thing we're gonna factor I out. So again, the I just kind of vanishes. Just what? Okay, not really vanishes, but we just put this out. So that, and I know we run out of screen, but again, we put the I in front, so we remove all the I terms, remove this, and then dot dot dot. I don't know. Oh, 2 equal sign. There we go. Now it fits on one screen. Barely. So, here is where this all kind of surmounts to. What is this? Oh, forgot. Let's go up. Isn't it this, but replaced with theta? Take a look. Yeah. So that is the Taylor series or Mclaren series for cosine of theta. Now, plus, again, we have this thing over here, right? I times, what is this? Again, let's go up. Does it match? Matches to me, we have theta minus to the third, plus to the fifth, minus to the seventh. Yes, you are not being fooled right now. This indeed equals sine of theta. Again, we're just replacing theta with x, it doesn't matter. So, what we just concluded is that e to the I theta, you know what, this deserves its own thing, equals cosine theta plus I sine theta. And that is how we proved it. That is probably one of the coolest things I have seen when I first learned it. And hopefully you find this cool as well. So, that kind of makes it to our home stretch here. If theta is pi, then we replace everything with pi. There we go. Just replace everything with pi. Alright. Here we go. What is the cosine of pi? Well, think back. Actually, you don't have to think. It's -1. Plus, what is the sine of pi? Again, the same thing. 0. I, right? Because we have this thing. Which then means that e to the I pi equals -1, because the 0i disappears. And finally, e to the I pi moves the -1 over, plus 1 equals 0. And yes, that in fact, if I can find the symbol, I can't find the symbol, but usually, you know what, that is, in fact, the proof of Euler's identity. And there we go. That is it. So, that is kind of, that's kind of like how we do it. And, if you enjoyed this video, please leave a like and subscribe. And I will see you in the next one. Hopefully you enjoyed.